All right, kids. How's it going? It's me, Uncle Starach, back with another video here to try to teach you guys the best I can through all this nonsense, I'm sure you're all happy to see me, and believe me, I wish the feeling were mutual. Okay, so just to go quickly with what we've been doing, we talked a little bit about the gas laws, and these are the three gas laws that we're going to use the most, okay? So you got Boyle's law, which is P1V1 equals P2V2. So the first pressure times the first volume equals the second pressure times the second volume. Now, Boyle's law is this one that we talked about. I tried to use this analogy. Let me just move this over a little bit, okay? I tried to use this analogy with the sponge, right? Okay, so if you increase the pressure on a sponge, pretend the sponge is a gas, the volume is going to decrease. But if you decrease the pressure, the volume is going to increase and the sponge will expand back to its normal volume. That's kind of how this law works. It's inversely proportional, meaning if one goes up, the other goes down. Okay, so if you increase the pressure, the volume is going to go down. Right? But if you decrease the pressure, the volume is going to go up. That's an inverse proportion. Okay, but Charles's law, I guess, this is what's called a direct proportion. Now, what that means is as one goes up, the other one's going to go up too. So what happens to gases, as long as you keep them at a constant pressure, if you heat them up, the volume is going to expand. So as the temperature rises, then the volume is going to rise also. That's keeping the pressure constant, of course. Also, whenever you're using temperature, either in Charles's law or the combined gas law, you got to make sure you're using the Kelvin temperature because the volume is directly proportional to the Kelvin temperature. Okay? So you got this one's inverse. One goes up, the other goes down. This one's direct, one goes up, the other goes up. Then there's the combined gas law, which basically, says what it is. You're just taking these two laws and combining them into one. This is the one that we're going to use the most. This is also the one that is the first sample problem that's completely worked out for you, all right? Now look, I don't care what pressure you use. I don't care what volume you use. What I care about is that you're using the same units, all right? So if your volume's in milliliters, you got to keep it in milliliters. If it's in liters, keep it in liters. If you have milliliters and liters, change one to the other. Just make sure you're using the same unit. I always had that analogy. I can't charge you for something in dollars. You pay me in euros, and then I give you the change in like yen or something. Everything's got to coincide, okay? All right, so let's take a look at the first sample problem that's in your packet. Obviously you would have a packet if we were in class right now, but we're not. We're in my kitchen, which is a little bit different. Anyway, so let's check it out. It says, we got to figure out, first of all, which of these laws we're going to use based upon the information that was given to you. So it says 2,500 milliliters of gas are on, it doesn't say what gas for now, it doesn't really matter. It does, but for now, we're going to just pretend it doesn't. All right, so we've got 2,500 milliliters of gas are under a pressure of 99,400 Pa, which is pascals, okay? So it says, what is the pressure in mmHg, millimeters of mercury, if the volume decreases to 1,750 milliliters? Okay, so we have the original volume and the original pressure. It then says, what is the pressure if the volume's decreased? Okay, it doesn't say anything about a temperature, all right? Since it doesn't say anything about a temperature, that must mean the temperature is held constant, and this is not going to come into play. At least not now, but it could in another problem. In fact, it will in some other problems. Okay. Think about it. If I increase the pressure on a gas at 30 degrees Celsius, and then I decrease that pressure at 30 degrees Celsius, the temperature has remained the same. It's not going to factor into the final answer. All right, so here's what we got. We got We know we're going to be using Boyle's law. P1V1 is equal to P2V2. Well, let's plug in what we know. Now, it says, what is the pressure in millimeters of mercury? Let's worry about that at the end. All right? Let's not worry about that at the end. Again, I feel like I'm like my father. I'm talking with my hands. And, oh, hey, how you doing? Okay. So let's see. The first pressure was 99,400 pascals. And the first volume was 2,500 milliliters. So let's just plug those in right now as is. So we got 99,400 pascals, that's pressure 1, and volume 1 is 2,500 milliliters. Now what you're going to find is I'm not really doing sig figs that much, kids. I'm pretty much past that. However, 99,400 without a decimal point would have 3 sig figs, and 2,500.0, which was given in the problem, was 5 sig figs, and we'd end up rounding to the one with the least. Okay. What is the pressure in millimeters of mercury if the volume is decreased? Okay, so we got pressure 2, which we don't know. Just call it P2. You could call it X, doesn't matter. But the volume is decreased to 1750. Now, before I even do this, I have to come out with a pressure higher than 99,400 pascals. And the reason I know that is because the volume's going down. If the volume's going down, the pressure had to be increased, right? The sponge, right? All right. So the volume for the, after the pressure is increased becomes 1,750 milliliters. And I have a very simple algebraic equation set up like this, okay? All right, so now what I'm going to do is I got to get P2 on its own. So I'll divide by 1,750 milliliters on both sides of my equation, okay? It's going to go away. And the only thing that's going to be left over here is P2. All right? But here, the milliliters and the milliliters are going to cancel out. So those units are going to go away, but the numbers are not. All right, so the pressure is going to be equal to 99,400 times 2,500, and then we hit equals, and we're going to divide by 1,750, and we get an answer of 142,000. How about that? It came out to be nice. 142,000. All right. Well, 142,000 what? Kitty cats? No. It's going to end up being pascals, or PA, because that's the only unit that's left. This and this canceled. The numbers didn't, but the unit was still there. All right, so pressure 2 is equal to 142,000 pascals. Okay, but the question didn't ask for it in pascals. It asked for it in millimeters of mercury. Well, if you go back one page in your packet, what you will find is that 760 millimeters of mercury is 101,325 pascals. Okay, kind of was running out of room there. I'm sorry. All right, so 760 millimeters of mercury is 101,325 pascals. Okay, so let's do our conversion factors like we did in the beginning of the year. So you got 142,000 pascals, and we'll put that over 1 like this, kind of like when we were going grams into moles, moles into atoms, or molecules, right? The old holy grail, right? Okay, 142,000 pascals. All right, now here's my conversion factor. And I'm going to multiply by what I'm looking for over what I have. I'm looking for millimeters of mercury, so I'm going to put that on top, and I'm going to divide it by the thing that I have, which is pascals. And there is 101,325 pascals in 760 millimeters of mercury. And what I get is a beautiful equation, kind of like this. It's actually not an equation, it's a conversion factor. All right, so here's my final answer. I'm going to take 142,000 times 760, and then I'm going to divide it by 101,325, and I'm going to be left with this many millimeters of mercury, 1,065 mmHg, and that is what the final pressure would be in millimeters of mercury, okay? So listen, everyone. The problem before that was the combined gas law. Now, I'm going to give you one of those to try. I might even give you two to try. It's not like you got a lot going on right now, right? Okay, so the one in the packet before the one that I just worked out here was a combined gas law, but here was the problem. Remember everything coinciding, right? I gave you, it says a sample of gas at 25 degrees Celsius and 102.6 kPa. So kPa is the pressure. But at the end, I changed the pressure on you to 0.943 atm. Well, it doesn't matter if you change kPa to atm or you change atm to kPa. What does matter is that you're using the same units. If you want to change kPa to atm, that's fine. You want to change atm to kPa, that's fine. You want to change both of those into millimeters of mercury because, I don't know, you're bored? That's fine, as long as both of the units are working together. And if you have milliliters, you better be using milliliters. If you have liters, you're using liters. But the part that definitely is important is that the temperature, whatever I give you as a temperature, you have to change to Kelvin by using the conversions I gave you in the other video. All right? So that's what we're going to do. I'm going to post a couple problems and then maybe like a video lesson like this to go over, or we'll do a Google Hangouts or Google Meets, whatever it's called, session, and we'll try to figure it out from there. All right, kids, hang in there. Uncle Starach is out.